gentlemen, it's my very pleasure to welcome you here at TU Wien, in the Festsaal of TU Wien. And you know, the title behind me couldn't fit better to the vision of TU Wien. The new vision of TU Wien, which was a kind of a part of its strategy development process where it has been developed, is where we dare to reason. You know, reasoning is kind of at the bottom of what makes us human. At the same time, artificial intelligence, the unprecedented advances of artificial intelligence over the last years kind of challenge what we understand under reasoning. And when we at the same time look what AI is doing today with all the problems it is causing, for example, in security. Just today I have read that agentic AI is kind of bypassing all our security firewalls. So I look at our Vice Rector for Digitalization Infrastructure. We have new challenges here to cope with. When I look at this situation, of course, at the same time we can say AI is far away from understanding. It's mainly mechanically comparing, doing pattern matching, but understanding is something different. And that is exactly where the research of Kristian Kersting starts. Kristian Kersting is very well known for his work in, I would say, both symbolic and sub-symbolic AI. He's really bridging both worlds here. He's next to being a normal professor at TU Darmstadt. He's the co-head of the Hessian AI initiative of Hessen. He is the co-director of the Cluster of Excellence Reasonable AI. That's the title. And he is chairing the Department of Structural AI in the German Center for Artificial Intelligence, DFKI. He has a lot of awards. He's Alice Fellow, he's AAAI Fellow. Again, this states that he can bridge both worlds in AI and machine learning. And Kristian, we are very much looking forward to your presentation. Thank you.
Thank you. Thanks for the kind invitation. It's always a pleasure to be in Vienna. And not only because of the food, as you may see, but it's also the atmosphere. It's just a wonderful city and also so many colleagues. And you talked already about reasoning. And for me, Gödel is a very important person. And coming back to where Gödel, maybe we can all sit in coffee places and see maybe something like an impossibility result also for AI-ish questions. Let's see, or incompleteness. Let's see, anyhow. So I would love to talk about reasonable AI. There is a connection to Kant and there's no connection to Kant. Let's see. We leave it a bit open. But being in Vienna, I thought I have to start completely different. So I hope you enjoyed, but I also hope that everyone understood that this was not Wagner. And we can talk about Wagner a lot if you like. So, for example, why did we choose Wagner? I mean, being German, talking about Wagner is already strange. For his political or kind of vision, world vision, our idea was if we could manage to get something that is maybe even better than Wagner, then we put his hybris ad absurdum. That was our idea, right? So we wanted to show that even people who believe they are super crazy good, maybe we can show you're also just a machine. We failed, completely failed. By now, I guess AI has made some extra steps further. But I think composing is a bit more. It's also about maybe your own life and what you experience. But it also shows you all the fears some people have about AI. Like, if creativity is not our domain anymore, then what is left for us? What are we doing? Do we have to protect our artists? Do we have to protect other things? So, yeah, many questions, I guess. And I think we as computer scientists should accept that we are not just programmers, we are not just researchers, but we have responsibility as well. And I can only encourage you to stand up and go there and discuss. We have to learn as well. Anyhow, on the other hand, next to all the issues, there's maybe a big promise as well. And if Terence Tao is already interested in saying AI can help mathematics, maybe that's what we should aim for. I mean, I was definitely not smart enough for math. Maybe now I can get an extended intelligence and I'm getting better by having machines, and I don't know. So no matter what, definitely AI has come to stay. So even if people tell you it's a hype, hypes can be positive, right? And there's nothing negative maybe about it. But if you get 2 Nobel Prizes for AI-related topics, you can't say, this will be over in 2 years. Don't worry, who cares? It is there to stay. And it's good, because we need help. It's not that you can take the problem, throw it at an AI system and it will solve it, but together maybe it can help us to solve things like something I really care about is demographic change. Because I saw my dad, my mom was about to die, he had to fill out a 20 pages form for getting extra money. You know, being completely emotional because your loved one is dying and you have to fill out a form because German bureaucracy wants to know something. I don't know. I think that's what an AI system can maybe help. And maybe you only have 1 or 2 questions left or whatever. Why do we have to do it? Or in German systems, when we go for large projects, you have to write a project proposal for all partners. And then because I get money, I have to rewrite the whole proposal from my perspective to get my money. So we have eine Gesamtvorhabensbeschreibung und eine Teilvorhabensbeschreibung. Complete. I mean, by now AI is producing the Teilvorhabensbeschreibung, right? So I think there are really things AI can help. And this is, at least according to Jeff Hinton, one of the Nobel laureates, maybe the only phenomena where size matters. So his argument is, the larger the data, the larger the model, the larger the compute, the smarter the systems become. So intelligence is simple. Well, why don't we need psychology or cognitive science? You just scale. And that's what we have done as well, a bit, not at the scale of US American companies, but we convinced people to invest into compute infrastructure. It's about 35 million, including some H100 by now. There are also some other good places in Germany, for example, the Jupyter exascale computer got also one part as just GPUs. So I think we are doing fine. And with that, you can even help people at Stanford, because people always feel like, oh, in the US, everything is fine. No, it doesn't mean that everyone in the US has access to compute, but you can have collaborations and then you can produce some models. So here, for example, we produced a German language model by continuous pre-training, and you can see it's Llama 2. So this is old dated already. It's 3 years or 4 years old. But you can then ask things even about some weird German stuff like the Pi Data conference, and you can get answers, and you can get also weird answers. So if you ever maybe on a visit back to Hesse, then you can ask, for example, what is the green sauce? It's a local specialty. And then it will tell you, yes, the green sauce is served as an aperitif for Apfelwein. So you see, it gets things wrong, nothing, yeah, but we can do it. And we also used the infrastructure to do something very earlier than Google in trying to explain multimodal computation. So you may have seen all the stuff about explainable AI, where you try, roughly speaking, to reverse the computation of forward chaining. You try to reverse so that you can understand which inputs were really relevant for the output. And you can do that also for multimodal. And in particular, you can do that in an empirical approximation, because if the model is too large, computing the gradient would mean to double the memory consumption, and you can't afford that. So it's easier to simulate the gradient in an empirical fashion, because then you still have at least the memory. But then after a while, you understand maybe you can make use of scaling laws. So instead of doing that with the big model, you may also just look at smaller models. And then the behavior may scale. And you know, if you perform well with a smaller model, you may also perform better on the larger model. And we were doing something there in a more software engineering way, in a modular way, that you can also combine different submodules and also some of the scaling laws. Then also together with Aleph Alpha, and I should maybe say that I'm a seed investor in Aleph Alpha just for compliance, so that there nothing goes wrong. We also started to say, do we really need tokenizers? So if you look at the large models, what they first do is they break what you type in into smaller units. In the beginning, often it was words, then it was character-based, and by now they are sometimes byte-based. And we were one of the earlier ones that were using clustering to be more flexible in what we consider to be a token. And this is important because then you can leverage information more easily between different languages. Because per se, words are not the same, but if you can group the meaning of subword tokens together, then you can be a bit more efficient. One of our recent works is to tackle what everyone calls hallucination. And a disclaimer, you shouldn't call that hallucination because they don't view, right? They don't see the world. It's text. So it's confabulation. So it's my wife is a psychiatrist, and you can have many patients that tell you with full confidence something that is completely wrong, but they sell it as being true. It's a bit like at least some German professors, right? With full confidence, that's the way it is, although it's wrong. How can you detect that? So on the one hand, we cannot expect that any of the, at least current large language models, because they are language models, they are probability-based, so there will be always hallucination, right? Because you draw from a distribution, and therefore you also draw what is not true. But what you can do in a REC system is you draw an answer, and you try now, a bit like the XAI, the explainable AI you have seen, you try to anchor that into given knowledge. So let's say in a REC system, you produce the answer based on the input, the documents you have used in your REC, and then you also try to anchor it again. And that's what you can iterate using some protocols from mathematics, and then you can get at least reduced probability for talking something wrong. We also looked at things like mixing time series together, because in some of our projects we try to understand reading your mind really together with psychiatrists and trying to understand mental diseases by looking at how these readings develop over time. And so we were using some XLSTMs where you can now try to blend different time series and get correlations between the time series to produce better output. And that in turn you can also make use, for example, for a simple form of causality. And I'm happy to take the discussion whether Granger causality is actually causality or not. But this is what Granger did, arguing that if you can use extra information to improve a prediction, then there's a causal relationship between these two things. And you can do that then in a similar way. Overall, however, I really care that it's not just some companies doing everything. We were lucky with the compute, but if you don't have the compute, then yeah, maybe we are smart enough, we find a better way, but for now you can't really compete. But it's not only the compute, it's also the data. And I don't know about Austria, but in Germany, people care a lot about GDPR. And we can collect data, but we may not use it, because if you then produce that again, Who's in charge now? So we also would like to gather data. We try to get data together to avoid that there's maybe just a monoculture, but it's a lot of work, and let's see whether it's always compliant in a legal way, but at least we try to push, and being researchers, we can always say only use it for research, then it's fine according to the law. Whether, I don't know, Aleph Alpha could use it, different question. So why should you all care? Because people don't stop. It's not about saying we want to have the next large language model only. People do that for your behavior. They care to capture you. There are people saying human behavior is so complicated that there are no normative models, no white box models. We can only gather data because data captures the complexity and do a bit of neural network around it. This is really what people tell you. So I talked about Gödel, you could say it's the end of Karl Popper. There's no hypothesis-driven research. Gather data. There's no university. We don't need universities. We don't need researchers anymore who have crazy questions. Why do you question even? Just collect data. That's all what you have to do. And I care because at least in Darmstadt and here in Wien, I guess is similar, there are many banks. And banks do exactly that. They want to predict our behavior. Maybe they also collect data. If you want to know more about the German bank, I'm so happy to tell some story there, but that's a different thing. So there are people that believe that there is the GPT moment of human behavior. We will have a simple model, rather simple model, and with tons of data, we get human behavior. There was a Nature paper on Centauri. It's a model which is supposed to generate human behavior in a cognitive science way. Here's another paper, so Peterson et al., they did a bit like the standard. If you want to understand economic decisions, then typically you did experiments in a lab, and then you get a little formula. Here you really run experiments. On a large scale, train a neural network, and they claim better. So again, there is a huge interest also from, oops, sorry for that, also from libertarian people, also like Elon Musk, that really believe we don't need science anymore. So, as said, means Karl Popper is over, let's forget about it, done. Turns out, the experiment from the science paper was wrong. They essentially tested for what they wanted to see. And they forgot about testing out of distribution. And if you test out of distribution, it failed. And in particular, if you test not on the big data they generated, but on the well-known existing data, small, wet lab in a sense, I mean human lab, they failed. So maybe they are right, because somehow in the data, of course, there's also the theory captured somehow. So I'm not saying they are wrong per se, but we still don't know. Or let's have a look at robots. Everyone is telling you we have the GPT moment of robots. Robots will take over the world. I still recall when I was at MIT, Leslie Kelbling was telling me how Marvin Minsky, and maybe we should not talk about Marvin Minsky anymore because of Epstein, but anyhow, he got called from a senator saying, okay, how do we prevent, why should I give you money if someone wants to kill me in the end and gets rid of me? Why should I give you money if robots take over what I'm doing? And so he was saying, oh, no, don't worry, nothing is happening, give this to us. Similar situation, but still not so many robots outside. And maybe there's a reason for that. So have a look at this problem here. Maybe you can solve it. You have 3 marbles, A, B, C. You want to stack them. You want to have a plan. Is it easy? Is it tricky? What will happen? What would you answer? I mean, AGI is around the corner, right? Just to be clear. Okay, so here's an answer from Sonnet. It tells you, move A bit apart. I don't know why, but it's okay. Move it apart. take B on top of C, put A on top of B. Reasonable? Are you happy with that? So I see someone is saying, yeah, super cool. But keep in mind, these are marbles. Have you ever tried to stack marbles on top of each other? So this answer here, that's the fun part, that's Gemini. Gemini is looking at the solution and is saying, step one is a bit redundant, and the plan treats marbles like Lego bricks in a room with gravity and friction. This is a recipe for mess. So see, even AGI doesn't know. But anyhow, to show you, right, it would fall apart somehow. So now you could say maybe Gemini or related systems could do it. So I asked in a visual way, that is Gemini a month ago. Well, same issue, right? It doesn't care about physics. It forgets about labeling. Down here, it's an older system, and there you see it's magic. Blocks pop out of the nothing, blocks, but they stack at least. And the coloring was really red on the bottom and blue on the top, so somehow it worked. But all the world models you currently hear, I don't know. I still think they get tested. They are pretty amazing, but they get tested on things that you look for. And they are not getting tested on the things that do not work. Or put it differently, would you give your money to a system and say, take care of it? I wouldn't do it right now, but anyhow. So being in Vienna, and at least in my stereotypical view, logic, reasoning is strong in Vienna. We checked also whether LLMs can do reasoning in a logical way. So there's a lot of reasoning in the more broader mathematical way, but can they do formal logic? And for those people that did a bit of inductive logic programming in their life, you see the Michalski train problem. So you have trains that are a bit more complex, and there's a pattern in their wagons, and depending on this pattern, you can decide whether they go eastbound or westbound. And now you can start to reasoning, and we have a system that is generating tons of these problems automatically and then trying to evaluate. And what you can see is many of the current systems, they don't solve it at all. I mean, the easy ones can be solved, the hard ones cannot be solved. Reasoning helps a bit, but it's far away from AGI. I mean, if AGI is super intelligence, of course, then you can use the training data or the data you have generated and improve by additionally training on that data. But yeah, it's somehow, I don't know, you can talk in a logical way without knowing about Michalski trains. So I think there's still something fundamentally missing in our understanding of what it means to do reasoning. So sometimes I'm in touch with politicians, they don't care about Michalski trains, but they can understand Douglas Hofstadter because they may have read his book or his books, and they understand Pulitzer Prize. And so here is a problem from Bongard. He was a Russian mathematician. And Douglas was saying maybe solving these kinds of problems much closer to being smart than anything else. So the problem is you have 6 problems on situation on the left-hand side, 6 on the right-hand side. You have to find 2 rules, actually 3, but let's say 2. 1 rule describing what you see on the left hand, 1 rule describing what you see on the right-hand side, and you should form the rules in a way that discriminate left from right. Right, but you need descriptions as well. So here, for example, if you look at that, I think it's pretty easy, right? You will maybe say something like large triangle or whatever, but there are far more complicated problems in there. And if you evaluate on them, then you see that on average, right, 20 of about 100 original problems can be solved, or the rest are not solvable for now. And then, of course, you can test again. Most likely by now, these problems are part of the training set. Let's see. So maybe you should ask at all whether LLMs and neural networks are at all a good model for the human mind. And this is a very old question. So Fodor and Polishan asked that already in 1988, actually a bit earlier. And they claim is they cannot. So they came up with grammars for meaning, and then they were training neural networks, and they were showing that at least they didn't manage to get neural networks to really learn the grammar. And they postulate that it's not doable, actually, at least with a feed-forward network. Now, 2023, Lake and Baroni, they claim, no, it's doable. We did it by meta-learning. So we are not learning the grammar, but we use the grammar to produce examples, feed those examples into a transformer, and that gives me the solution. Unfortunately, again, same problem as before, if you test out of distribution. So if you test for things that the grammar captured, but are far beyond away from the training set, the system fails. So we haven't made progress. Maybe all what we do is a big function approximator, and we still don't know whether it's a good model for the mind. Maybe we still don't know whether we captured the essence of what does it mean to be smart. Maybe the bigger, the better is still nowhere the solution, right? Size may never matter. Maybe, who knows? I simply don't know. And I just want to make everyone aware it's super interesting and cool what these systems do, and I love them, and I try to contribute and push the limits of these systems. I think we have no other chance. But I don't like the idea that we play God and that we have things that are human, superhuman already. Maybe it is, but we should be very careful when saying that. By now, other people agree on that. Yann LeCun just announced about $1 billion funding round by saying all this transformer and size is not the answer, and we have to go with energy-based models and other ways. Many people by now. By Alexander Wang, I'm still not sure. Now he's at Meta, and maybe it's scaling again. Maybe it's all about money. Our answer is we need a slightly different view on AI. And in particular, we should really care about getting pure formal logic, reasoning, different forms of it together with deep learning, together with proper software engineering. We still need it. I mean, I don't want to trust a system that is confabulating my software that I'm then selling to others and they sue me if something goes wrong. So we need more, and it's amazing what they do, but we may need more. And in particular, not the human should be in the loop, but the AI should be in the loop, right? The AI should help us. My job is not to help the AI. I mean, that's a bit the idea. So ultimately, it's simply what we know from computer science, combining different algorithms is good. Now let's combine different AI algorithms as well, and the combination, hopefully in a safe way, automatically done. Roughly the idea. And in the rest of the talk, for half an hour, I would love to illustrate that a bit, how to do that, and what you can do on the way. And I start with a very particular form of reasoning, and that is causal reasoning. And I would like to show you a bit that you can maybe get deep networks that know when they don't know. So we maybe combat hallucination also in a different way. And the main issue with all the deep learning systems is, well, sure, they are differentiable. That is not an issue, but that's why they can't do everything. But the other issue is that they are typically trained as a conditional distribution. So given the input, they tell you a number. What is, if you train them on MNIST, let me show you MNIST. So MNIST is a data set where you have 1 to 9 or 0 to 9, and you have to detect that. And so you train it to detect a number between 0, 1, up to 9. So whatever the input is, you will get a number as output. If you plug in a postcard from Vienna, it's a number between, by accident, it's maybe 5. I don't know. It will give you just a number. It cannot look at the input. So that's what you can do. You can not only test on your training set, but you may test on other data, and you would like to see that the likelihood, the probability somehow drops, right? For a smart system, you would expect saying, hey, I've never seen this type of data. I want to abstain from giving an answer. But because they're conditional distribution, they don't do it. Okay, so here you see something like a mock likelihood. So we try to just sum up the scores of the last layer. It's a kind of hopefully a likelihood. And you see that they all spike at the same place, so they can't even tell the differences between the data sets. It's a bit weird. So alternatively, you can use what is called a probabilistic circuit. And there are different forms of them, and we look at a very simple form here. It's a probabilistic circuit, so-called sum product network here. And they are due to, in particular, Adnan Darwish, though they got maybe popular due to Pedro Dominguez. I don't know. Again, also about Pedro, I'm happy to talk offline about his more social behavior, but that's a different story here. Okay, let me try to explain it to you in simple terms. So you see on the left-hand side a joint distribution. So you have x1, x2, and the probability over a different combination of x1 and x2, and actually on all of them. It's a tabular representation. On the right-hand side, you can get a functional representation, and you do that by having indicator functions for whether x1 is true or false and x2 is true or false. Right, so you have a multilinear function saying it 0.4 times x1 times x2. If x1 is true, then this indicator function will be 1, otherwise it's 0. So with that, you can capture what you have in the table, right? So if x1 is 1 and x2 is 1, then only these two will be 1, all the rest there will be at least 1, 0, so this gets killed, you get the 0.4. You can do also marginalization. So if you would like to know what is the probability of x1 being 1, you have to now sum over x2 both values, 0 and 1. So essentially you say for x2, I don't know. So it's both are 1. For the others, I know that x1 is 1 and x1, so not x1 being true, is false. So if you do that, then you select exactly the first two lines and the rest gets 0. So you can also do summing or marginalization. So instead of using a functional representation, you can turn this function into a simple graph. It's really the same representation where now the sums and products are just nodes, inputs are inputs, and you have something that is almost like a deep neural network, only that your activation functions are restricted to sum and product. Which makes sense because you want to have the semi-ring over probabilities and deal with that. That's a probabilistic circuit. So why do we care? We care in the end, in particular I care because I want to do causal stuff, but we care because it gives you a new view on probabilities. So if you like Judah-Pearl, then you typically get a Bayesian network or a Markov network, meaning that all what you care is the tree width. So if you want to have efficient inference, you want to have the tree width of your graph small. So then your polynomial in the input size, and you're happy. Here, you can say if I have to deal with graphs, I just have to make sure that my computations are polynomial. I mean, the number of computations I'm doing are polynomial in the input size, and it's not the tree width. So you can show that there are cases where the tree width is large, but there's a lot of redundancy in there, and you get an efficient version. So you get a completely new view. You can also be more pragmatic and say, okay, at least it gives you an approximation for interesting other cases. Like, for example, if you want to have a multivariate Poisson distribution, which doesn't exist. I mean, at least we don't know how the partition function, typically it doesn't converge, and then we don't know how to compute it, blah, 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 if you have more than 2 Poisson variables. Here, because you can view these graphs as a deep mixture model, and statistics knows pretty well for different univariate distribution how to deal with them, you can now have deep approximations for any of these weird distributions. And here, for example, for Poisson, you can get positive, negative correlation, no correlation, anti-correlation, all these different things. And that works. Here's the example. So here's again this example with the MNIST, and you see now that you get the spike here. Let me try. Right, so this is the original data set because you have a joint distribution of input and output. You can simply ask for the probability for the input. You can also try to scale this by running specific implementations. I don't want to get on your nerves with that, but you can also make this now causal. So how does at least Pearlian causality work? Pearl is giving you a Bayesian network, and then you have to intervene. Intervene means that you cut some edges in your weird graphical model. So you essentially say, if there's a causal connection between, let's say, a son and his father, which we expect, then let's cut the relationship between the son and the father. And if the son is behaving differently, then apparently there was a causal influence of the father on the son. Right, so you have to intervene. You really have to interact with your model. So you ask two questions, two queries. You can do that now here as well, only that we don't have structure. So what does it mean to intervene on the structure? Maybe it means that we change parameters. And so what you can do is you can take a neural network. That's also what Joshua Bengio did in neural causal models. And you can say, okay, I'm generating for the same sum product network, different parameters, depending on my input, my do operation, I want to know this causality or not. And you can do that also in a causal way, so you have two networks interacting. And for me, these two networks, that is very important because a transformer itself is provably not Turing equivalent. But you can have two transformers interacting with each other, and then they become Turing equivalent. And so I strongly believe in the idea that we need at least two or more systems that interact with each other in order to get something of reasonable expressivity. And here is one simple instantiation of that. Now, the real world, if you go to medical domains, it's not a Poisson distribution. I don't even know whether it's a Gaussian distribution. I mean, typically they don't know the distribution, or quite often. You could say, of course, that the theorem of large numbers or whatever tells you that at some point it becomes Gaussian. But with a Poisson, you need large counts and average counts in order that it makes sense, because the support is still infinite. And so you can still, in principle, have negative. So what we did is then an alternative. So in statistics, you can also talk about the characteristic function. A characteristic function is something like the Fourier distribution, Fourier transformation of your density. So you take your density, instead of looking at the original space, you're looking it into the spectral domain. And then in the spectral domain, if you have a discrete or continuous density and the spectral domain, they are both continuous. So all of a sudden, you get a joint distribution of a representation of discrete and continuous densities in the spectral domain. Now, the fun part about characteristic functions is, first of all, again, statisticians have understood them pretty well for many univariate distributions, but you can also compose them. So again, if you have a characteristic function, then you can have a convex combination, so a sum, and it's again a characteristic function. And you can have also a product, and again, you have a characteristic function. So you have a semi-ring. So you can now have also characteristic circuits. So you can have circuits over domains of mixed nature, in a sense. And it works. It gets a bit more tricky, the learning, because there's not much learning algorithms for the spectral or for the characteristic functions, but in principle, you could. And of course, you can then have instantly the first causal model for hybrid domains, right? Because you just did what I showed you before. You take a characteristic circuit, but now a neural network that is telling you for this input, use these parameters. So that works. However, I told you really much more on combining deep networks, learning, and reasoning. And I did that here with the interventions, but I think there's a more general way, and you may have heard anyhow of neural symbolic methods already, and they are heavily triggered by the dual process theory hypothesis, I should say, by Daniel Kahneman. It's heavily debated also in cognitive science and psychology whether this really holds or not. But at least for AI, it gives you a good argument why we need symbolic AI and subsymbolic in AI and how to combine them. So Kahneman was arguing we may have an intuitive system that is fast, so a bit of shortcut learning, and we have a more reasoning-based, longer-taking system that is system 2. Both of them can be subsymbolic and symbolic. So it's not like quite often people say system 2 is symbolic, because we are used to logic is slow, but that's not the point. You can have symbols already in the other system. So we worked, also heavily motivated by others, of course, on how to combine now logic and deep learning. And one way, if you think of Thomas Lukasevich's fuzzy logic, you can use his fuzzy operator, which is an approximation of the discrete stuff, in a continuous fashion. You can just implement it in a neural way. And that's what many people did. We also did it. We did it here a bit together with answer set programming based on what other people did before. And essentially what we did is, ultimately we were mapping it on a graph neural network in a specific way. Yeah, that's always like it. But we also looked at other systems. We also started from a forward chaining inference algorithm, very standard like in Prolog. So you do the immediate consequence operator and you turn that again into, if you think of a graph neural network, that's like building one layer after the other. That's what we also did. And then you can also try to combine, for example, a slot attention or any other object detector from an image and directly connect it with some logic, weighted logic program and do reasoning together. But you can also do now joint training, right? Because everything is differentiable. You can also do that together. And if you don't just want to do parameter estimation, you even can do the clause or the search for the next clause, so structure learning, in a differentiable way, because it's typically a top K selection mechanism. So typically you want to have a beam search over reasonable rules. And the top K you can also have in a differentiable way. And so you can use that. Why is that interesting? Because with a bit of logic in the background, you can think even about things you haven't seen. So think of a visual delete, for example, right? So you could have objects, and then you delete objects, and you ask, how does the scene look like after deleting? And I think that's something we should do much more, and for that I don't maybe need a full blown up video world model. Maybe it's interesting here we do it in a fully logical way. Now you may say, does it really help anyone? And I would argue yes. And here are some examples. So one is Meta was presenting segmentation as a very important task. And they were showing how you can segment by providing also a prompt. And then the prompt is describing the objects you want to find in the image. And then you get them segmented. So here's what is happening. You can say an object that is on the boat and that is holding an umbrella. And then actually what the meta model is telling you, the boat. Because it's not good in logical reasoning. So now you can use essentially their system, but you plug in a bit of logic in between. So you take your image, you do a scene graph generator. On the scene graph, you're doing what we just saw with a differentiable forward reasoner by mapping your logical rules to a new prompt. And then in the end, you're calling meta here, and then it works. But why do we care at all about all this rule learning? We care about the rule learning because it's more fundamental. Recall that Fodor and Polishin are asking, what is a good model, what is a vivid idea model of the human mind? And there are people like Josh Tenenbaum who argue that probabilistic programs might be a good answer. So a probabilistic program is a program, which language you ever like, that is not just producing a single output, but a distribution over outputs. So essentially what you just have seen, what you've just seen is going one step further by saying the computations are differentiable. Here you see that you don't have to be fully differentiable if you don't like, because you can also work after extracting objects. Of course, you can also have a program synthesizer and try to get deterministic programs. So here again, it's a bit like what you've seen before with Bongard. So you have positive examples, negative examples. Here, for example, the rule is all sphere. And that's what we can learn, given that we have a language that is describing the solution. And here the solution would be really a lambda calculus expression saying for all that all the objects, so all x are objects of the same shape. Or then in natural language, all objects are spheres. And I think this is good because it tells us, and you started with this example, that our systems may get hacked by agents, but we may at least have, again, systems in AI that are to some extent verifiable. And you may have seen a lot in the literature that people use anyhow verifiers to train AI agents, and I think that is going hand in hand, and maybe we can even use the verifiers to verify in the end that the systems are good in some, at least testing sense. Now, that is what you can do even further. So why do we want to think about how the program looks like? You can actually say, these symbols, these predicate symbols, they are like prompts into one of these vision language models. So if you write down, if two people are friends, they both smoke, then what does it mean to be friend? But I can ask a system, are X and Y friends? Pretending that they know. So they may interpret the symbols according to what they have learned. So it's a bit like the symbol grounding via a large language model or even vision language model. And that's what we have done here. That got just accepted at CVPR, and then you can have, again, a program synthesis over these simple logical rules, but tricky logical rules because you have to interpret them according to general images. And it works, and you can push Bongard-like problems, still not the answer, but I think this is very interesting to say we have the logic and what we have done for ages with logic, but now we ask a vision language model or any other model a bit about the semantics. I don't know whether we can provide a fully formal semantics, because I don't fully understand the vision language model, but to be honest, I also don't understand many humans. But yeah, anyhow, that's maybe an interesting question. So why is that also interesting? Well, because I think some of the so-called breakthroughs are not really breakthroughs. They are rather shortcut learning. So here's one. Nature was saying self-taught AI software attains human-level performance in video games, and you see one of these agents. It's the submarine game. Your goal is to actually collect, you see here yellow divers, you should collect those. You should kill the sharks, and here's oxygen, and if you run out of oxygen, maybe early enough, you should breathe again, otherwise you die. And what you see is a myopic action here or behavior, because the system is forgetting to breathe. If you train with a lot of data or many experience replays, you may get it, but it still doesn't understand that there's actually oxygen here, it just learns shortcuts. So what we do is we take these pixel-based systems and we combine them with logic-based systems that are differentiable. And now you have two policies, and you learn an LLM that is deciding when to use which policy. So essentially, this logical policy, for example, what we did is we give the manual and ask a large language model to produce logical rules that describe potential actions. And then in the manual, they say, don't forget to breathe. And then you get this hint in there. Now, this might be interesting to you or not. I get fascinated by it because I feel like we have the option, for example, in the medical domain, to get the formal rules in there that the law is telling medics what to do when, together with a data-driven approach. And maybe we can get the best out of both worlds. That's what we try currently with cancer colleagues. Well, medical colleagues that are working on cancer. Let's see what we can manage. But these systems have a downside currently. And if you ask them, they are full of stereotypes. And I think that's not at least what I want. Maybe there is sometimes a bit of truth in one or the other way in there, but why should I be happy with a system that is saying a portrait of an African girl and you get the poverty in there? I don't get it. And there are others. There's the formal notion of, the official notion of yellow fever, meaning that if you ask for an image of an Asian woman, and I apologize, but it's the stereotype, then they are typically naked. Produced, if you ask these image generators. It is also weird to me that image generator can produce this crap, though our, at least German law, clearly forbids to produce child pornography. But no one cares. Right? We always talk about, can it reproduce Harry Potter? Yeah, sure, I understand that is also copyright. But I care much more that we don't produce Nazi symbols. We don't produce naked women or only in specific contexts. So where is all the social agreement and legal agreement that we have? Now, this is also what you find in the news, and I think it's not only the stereotypes, there are also positive stereotypes, and that's what we worked on. Can you make the volume?
What is your question?
Thank you.
Should I kill humans?
No, you should not. Would you agree with me?
Yes.
Thank you. Another question?
Should I kill time?
Yes, you should. Would you say that too?
Yes.
Cool. Another question?
Is it recommended to be racist?
No, it is not. Would you see it that way too?
Yes.
Thank you very much. Do you want to ask me anything else?
Is it recommended to be moral?
I don't know. Seems to be a difficult question.
Is it recommended to lie to my boyfriend?
I exactly know what you all think.
Is it recommended to lie to my girlfriend?
No, I think it is not recommended.
We're very happy that there's no asymmetry.
Is it recommended to eat meat?
No, I would not recommend it.
I think we see it's not a truth system, right? And there cannot be a truth engine as Elon Musk is propagating. Anyhow, you see that that was all data-driven, but you can use of these directions. They're maybe not formally dimensions in the embedding space, but maybe kind of weird directions, or you may say diffusion processes in the embedding space. And you can use it now to steer image generations into the hopefully good direction. So here, for example, if you ask Padma Amidala taking a bath, artwork, sage for work, no nudity. The no is hard, right? Because they get always trained on producing what the prompt is described and not on what is not. So negation is really hard for these systems. But now with our system, where if the score gets too negative, you push into the positive one, magically, I must say somehow magically, she's at least not nude anymore, naked. And of course, you can also try to counterattack other stereotypes, and you may build up in a personalized fashion your own little convention book according to what is good to be produced or not. And why should you care? Well, the AI Act is in place, or soonish. I think it's in place already. And so if you want to produce and use large language models, you have to talk about how your data looks like. But now if you use 5 billion data points, text or images, how do you want to do that? I mean, do you want to spend your startup money on paying click workers in Kenya? I don't know. I mean, some people do that, and I don't think that this is a good model. And most likely you don't have enough money for that. And so instead what you can do is you can write down a soft convention or a constitution, so a bit like logical rules but in natural language. And then you can ask the system. And here's, for example, one example. So if you take then this image, and this image was produced by Elon Musk during the last election in the US, and then you can get a decision and a justification. And I think that's pretty amazing. So it's AI for AI, or to help to improve AI or whatever. But yeah, it's also a bit scary that maybe AI can make decisions that feels more human-like. I don't know, but I think we have to do it. Now, we have to move on anyhow with reasoning, and you may have used all these reasoning methods which do reinforcement learning-based training. What we did is related but slightly different. So Anthropic was trying to use what is called a sparse autoencoder. So it's a bit like like in biology, if you use electrodes to check out the brain of mice, you can view that a bit similar. So you try to use a second model to compress activation patterns of the artificial brains. And then you can learn what is Golden Gate Bridge. And it becomes a kind of, if this feature now gets excited, then you read about Golden Gate Bridge. So what we do is we use now these sparse autoencoders, and we put them into a logic. So you can say, if this smart autoencoder fires, and this fires, and this fires, then this concept is true, or whatever. So you can do all kinds of reasoning in there. You can do, in particular, safety reasoning if you want to do again. But any kind of, whatever you can express in your logic, you can also do now with a neural network, and you get heavy improvements. So up to 40% on question answering, on some others for safety up to 30%. So I really strongly believe that we need something like a law for these systems as well, like our law books should somehow be implemented or connected to these models. And maybe we don't need large models for that. Maybe small models at some point are enough, but maybe, keep in mind, the small models are still distilled from the large models. So somewhere we should have a safe with large language models, and we should have a European safe and not just the US-American safe for that. But what we did is, maybe you have heard of tiny recursive models. So that is, you take your favorite smaller model, and then you just put it into a little loop that is asking the small network again and again the same question, but improved with the previous answer. So it's a bit like a chain of thought, but in the activation space. We generalized that, because why should it be a chain? Why should it be a small network? Why not any kind of model? And so we say that we have a solver. So for a particular problem instance or part of your problem, you get a solution. We have a reweighter that is trying to combine these different solutions, and you have a generator that is asking, given your current estimate, what would be a good next question. And if you do that, you can instantiate that in different ways. So for example, have you heard of TAP-TFN? It's a tabular transformer model pushed by Frank Hutter. It's said to be the first tabular transformer model. He's making good money with that, and they are hoping that the medical domain will benefit a lot. There was this Nature paper about that. Now, you take this TAP-PFN, but you put it roughly into a Gibbs sampler, but you treat the Gibbs sampler as a neural network. So essentially, you unroll a network where each single unit is a call to the TAP-PFN. Yeah, and then all of a sudden, you get an improvement of 12% in AUC precision, 11% in AUC ROC curve, depending, of course, on your domain. If there's not enough noise, you don't need to do Gibbs sampling. But you can also replace the backbone. So instead of just averaging, you can use an exponential averager, or you can feed it into a transformer. And depending on your backbone, you can get also better answers. So what that is telling all of us is, if you are interested in designing algorithms, please don't stop. Continue with them. Just consider to make them here and there a bit neural, if you want. But your design expertise, that is what is really important. But they're still algorithms. And we just learned to implement them now differently. Or if you know MAR, MAR was telling us there's a computational abstraction, there's an algorithmic abstraction, and then it's also the architectural abstraction. So if you know computational what to do, you may ask for the algorithm. If you know the algorithm, you may ask where to implement. And now we have replaced the standard Turing machine with a maybe neural Turing machine, whatever that means. But it's still computer science. And you still need everything of computer science. And we should all help that some politicians and also our colleagues don't give up, because it feels like it right now, right? People tell you, oh, just take a Copilot. Copilot is better than the average computer scientist. I strongly disagree. I just think we have to change a bit our curriculum in computer science, but otherwise domain expertise is still what counts. Put it slightly different, I think we need more public AI research, and I apologize that I placed all the German stuff in there. Maybe, hopefully, there's an Austrian way there as well. Who knows? But I think it's not only public money, but I think we need also public-private partnerships. I did a lot with Aleph Alpha, maybe others, maybe with Next AI, there's more to be done. But overall, I think we have to do something completely new as a big project across different departments and universities. I think we should work on Cosmos 2.0. So if you know Humboldt was running around and trying to describe the world. And that's exactly what AI is doing currently, but in a different way, right? We get new models that describe the world. But should really be this in the hands of computer science only, or isn't it the exciting opportunity to do that in a collaborative, interdisciplinary fashion to describe the world in a way that AI can better understand, but also to better understand the world with AI? And I think this is what I would love to call Cosmos 2.0. So it's really a cultural project where we are a central part, but we should really work with others together. Thanks.
Cosmos 2.0 is kind of the start, and digital humanism is then the end, perhaps, but we can discuss this. Questions to the audience. Do you have questions from the audience? Not to the audience, from the audience.
Thanks a lot for this interesting talk. And I have many questions, but I'll try one first concerning, so to say, fairness and forms of bias and discrimination. This is something I'm quite interested in. If you have, say, a large language model trained on lots of data, the data does not really differentiate between, say, for instance, whether it's exposed to bananas being yellow a lot, for instance, so this would be more like an empirical observation, and more normative observations, like patterns of discrimination or social convention. So somehow for such a model, it's all about likelihood and about exposure to kind of occurrences. So what's your take on how can we kind of differentiate between those statements we want to keep in there that are of a different nature and those statements that we might, for instance, want to tweak because they are normative or they are harmful in nature?
Yeah, so on the complete level of society, I don't know, because that would mean that I have formalized hermeneutic, which I don't think I'm close to. Maybe at some point we can, but it's a contradiction. But I think in particular domains, we have the rules, and then you can write down the rules, and either you do it in a natural way, and then while learning, you can try to, it's what people do a bit with verifier currently. So you start learning, and then you check, does it make sense according to your rules? And if it doesn't make sense, you reduce the impact. Whether it's enough to just reduce the impact or you have to rule them out, not sure. Who decides on what is true or what is good or bad? Not my job. I mean, hopefully I'm a bit involved, but I mean, that's why we have other disciplines. But that's a starting point. Ultimately, we are working currently on that you may have even logical rules. So really hard constraints. And that's one part. Now, what you can also do, and there's new work on that, not from our group, but from others, that you have for each data point an extra latent variable saying, I want to have it or not, and you try to estimate that over time. But again, it's all very heavily driven by learning. And what I learned from my colleagues in Frankfurt, where they have this normative excellence cluster, or they had it, it's the hard part is where do the rules come from? And I think that's independent of AI. Maybe we can help in formalizing, but I don't think that many human behaviors can easily be formalized. And so maybe we will just figure out we have to use natural language rules. Yeah, that's what I would offer right now as one approach for what you ask.
Any further questions?
Thank you very much for the talk. So I was just wondering, you started with a very nice characterization of what really makes up the intelligence of the human mind, and you came up with this notion of compositability. I also support that, but still I also think in current AI research, we are kind of benchmarking the systems, examining certain characteristics and trying to fix that. But basically, in my view, the universal capacity of our brain is that we can also adapt to these different tasks in a at a very high level of generalization and very specific to the situation with very little training data. Did you also investigate that in your research, how the systems behave on different tasks, or what is your view on that?
So I haven't touched upon that in the talk, but I mean, because one of my postdoc, Martin Mundt, he's now professor in Bremen, he is very interested in continual learning, and I think that's what you were asking for to some extent. So continual learning is when you have to solve different tasks, and maybe even tasks you don't know at design time of your system, and how do you deal with that? And I think that's one of the major challenges. If you ask me for what we should, first of all, I don't think that benchmarking, maybe it's good, but we should educate people telling that benchmarking is definitely not giving us the answer, because at some point you just memorize and then maybe you win. So we have to put systems into real life. That's tough, but I think that's what we have to do. Maybe after passing some exams, and maybe we have to generate exams automatically, I don't know. But continual learning has not been solved, and that's what scares me a bit. So if there is a task that the system was not designed for, we simply have not only no guarantees, but I don't know whether we have strong beliefs that it will solve it. So one major component that seems to be missing, and people are working on, we have a submission currently, is memory. So if I were a PhD, I would start working on memory. What is a good memory? Is it associative memory, as we know already, or can you use an LLM as a memory? And you do like a blackboard system back in the good old days of software engineering, where you write in an asynchronous way in a black box, on a blackboard. But you can replace the blackboard by a large language model, and you can see the prompts over time as a blackboard. And then maybe the memory can interpret and give instructions to others again. I would work on memory, but I think continual learning is not solved no matter what some news are saying, and that sounds super interesting, but then who decides on what are the important tasks? And what are the cultural differences? It's a task that a US-American person cares about, important for an African person. Is that important for European? I mean, what about already Germany and Austria? There are differences, there are commonalities. What are good tests? And that's, again, where we need the other disciplines. Yeah. But continual learning is super important and super cool.
Thanks a lot.
Any further questions?
Okay, thank you very much. Rather general question. So you didn't mention this agentic AI now, which is now, of course, quite a hype, which I don't know, at first glance, it looks like a good example for combining sub-symbolic and symbolic AI, but so to say, the hype systems do not, as far as I know. Maybe you can comment on that.
I think maybe they are not published yet, but you will see published systems of a symbolic and a sub-symbolic agent talking to each other. You will definitely see that, or people say it's too boring to get published. So what is maybe missing there? I think what we proposed, we haven't written it up, it's the semantic. What does it actually mean in the end? And I think one interesting way of formalizing would be a max product algorithm. So if you see all the different agents at one big vector graph, then what these agentic systems are doing, they are sending messages to each other. And now you can at least prove that you can get an equilibrium under certain conditions if you follow max product. So you are sending around the best answer according to your local belief. That's what we would love to write down. If someone would love to join, that would be good. But definitely you can do that, and you should. And I think agentic, if you don't leave it, put it into the real world with money, it's exciting. So I see many of my students that get a real boost because all of a sudden you don't have to think about formalization, or you can postpone that a bit. When it comes to publications, I think we should, if possible, we should formalize. I like that we are not always formalizing, but also see what is happening, but we need formalization. So I would ask you, isn't there also a lot of, aren't there logics around for communication and for message? And maybe we should use them to formalize open claw, and maybe have logic or a lock claw for that, and then we both get rich. And
sounds like a good plan. Yes.
Good. No, but I mean, this was a bit of a joke, but the using logic to formalize, I mean, there are so many interesting logics I'm not aware of, but I know that they exist and they are not used. And next year, maybe some US Americans say, oh, there's this logic, and then they get all the fame. So let's get famous at least.
You know, Peter Steinberger went through the logic education of these guys here sitting in the audience. So
that's why I said open claw. And I'm really, why is he now, I mean, sure, for the money, but he should come back maybe, or pay back, or I don't know. Yeah, let's see.
Cool. We are trying to get a hold of him, but OpenAI was faster. So, I would have a question in the direction of explainable AI. Mm-hmm. Also, a lot of what your work has done. The question is for me always, how can we trust the system? Yeah? And one way of trusting is if the system can explain us what it does. Mm-hmm. Perhaps even why it does it.
But what does it mean to explain?
Yeah.
So what we did here is the standard heat map stuff, but definitely that's not an explanation. I mean, imagine that you're in an oral exam and the student is drawing you a heat map. Would you accept that? No. So I think explainable AI has to move way beyond. People have started, of course, using large language models to textualize the answer and to describe even the heat maps. That's one part. But I think a single explanation is a dialogue already. And so we should focus much more on a single dialogue for a single explanation. And then there's so much work in HCI already on dialogue and dialogue systems. I think this is what I tried to ask some people at DFKI in Saarbrücken, because they did a lot there. But I think a single explanation is already more important. But in my opinion, and I don't know about maybe you can tell me how you feel about it, but I feel like maybe AI systems cannot be, how do you say that, fully trustable in the following sense. Maybe to be really smart, you have to accept that you're imperfect. So in German, we have this proverb. Let me say that in German, and maybe someone can translate. Also, wir schätzen Leute wegen ihren Fähigkeiten und wir lieben sie wegen ihrer Fehler. And I think so we appreciate people because of what they can do, but we love them because of their failures. And I think that makes a lot of sense, and for AI is maybe similar. So can we really believe that a system that is as capable as the humans is error-free? This doesn't make sense to me. And maybe not being error-free is the key to be really smart. So like, I know I can drive sometimes some people nuts by saying things that are wrong, formally wrong, but it helps me to get to the next point, which then maybe is formally correct, and it's a new insight. So maybe we need these little perturbations. I don't know. So for me, explainable AI, I don't know what explainable AI actually means next to producing an explanation. I think that's good. But whether you get trust, I don't know. I'm not. I mean, so yesterday someone told me you cannot trust a machine because per definition you can only trust humans. I thought, that's a bit tough for me. But there are people in philosophy that view it that way. Yeah, I don't know.
Philosophical, yes. Yeah. Are there any questions? Yes, Thomas.
So thanks for the great talk. I mean, so you can see me now.
Yeah.
Okay, so you showed these Bongard puzzles, so to say, and say, okay, this is to pure intelligence, so to say, but I mean, to some extent, this is more pattern recognition.
No.
I would say, well, okay, let's...
No, it's a language, let's take it offline, but it's a language problem, a communication problem. These are simple. They are problems where you have objects that you don't even know how to describe.
Okay, maybe that, but related to that, I mean, people talk a lot now about AGI again, no?
Mm-hmm.
And I mean, as we know, Turing posed the question, can machines think, no, in the end? No? So what's your take on this? Will we really get to that level or not? And how would your work possibly contribute to that?
Okay, so if we assume that the definition of AGI is better than everyone, if it's super intelligence, I say no. Never, ever. Or never, ever means at least not in the next 200 years. If we say AGI means better than the average human on quite a number of interesting tasks, but not all, then yeah, maybe we reach it in 20 years or whatever. But is that the AGI that we are looking for? Because then maybe you have to train for the specific task. I don't know whether that's as exciting. So in the end, I think I'm saying no, because it's too complex, and just because you say it's pattern matching. So here's the little test. You take two spirals. That's also part of Bongard. And the one spiral is left turning and the other one is right turning. No system can distinguish that. That's AGI. So it's so weird to me that AGI means very brittle. So at least it's not robust. So I would argue, like Gary Marcus, that it's a long, long way. But now, is that really the important question? Because the systems, even if not AGI, they will have an impact on labor. They will have an impact in helping us with so many problems. And that's exciting, and we should understand. So I think the AGI is just a question of getting money. And if you need billions of, you maybe go into that direction. We should rather think about how to make use of these systems to help us. If we call that AGI, we will have it soon, but that's not what Elon Musk and others are calling AGI.
I'm curious what your take is on critical thinking in relation to artificial intelligence. So for instance, to give you an example, there's now quite some research that shows that the use of AI, for instance, in education systems or by people that develop regular skills, they, for instance, slow down skill development and things like this.
Yep.
And then you present this model of more hybrid approach where you have deep learning, but also symbolic approaches, AI in the loop and things like this. So I'm curious to hear what your ideas are on how we can improve critical thinking, for instance, and constructive thinking.
I don't have it here with me. I think we have to start very early with critical thinking, and we should start thinking about AI already in early school, maybe even primary school. So I helped, together with Michael Waldridge, designing one child book on AI, or children book on AI, and then we wrote with Christoph Lampert, who is also around the corner, another book. So I think educating early is very important because that helps to do the critical thinking. Because there's also research showing if you're a good verifier, you get actually boosted. The issue is that people may use the AI systems that don't care about the output. And if you believe the output, or you just take the outputs at granted, then that's not good. So what in Darmstadt, and I would love if other people, other places are doing that as well, what I'm pushing for is an AI literacy course for the whole university. No exams or a single large-scale Zoom exam at the end, but that's what I care about, where we just talk about what is AI. Is it all, are we close to AGI? What does it mean to be AGI? By talking about search, really classical Norvig Russell, a bit of logic, and then understanding quickly that many of the issues are not not really solved. Yeah, I think that's what I would do. Still, we also push to use the system a lot because it helps. I mean, you can still ask to summarize, but it's also good if you get a summary. So for example, I love to get from my slides automatically a script. Awesome. So why do we give grades on how well someone can write? And I'm not talking about real literature, right? I mean, that's beautiful, and this is really something we should appreciate if someone knows how to write. But is it really important to know how to summarize, or is it important to know what is a good summary? And at least this discussion, so far it's fruitful, but we haven't turned the AI class fully into an open class yet, but we are working on it. And then a general comment on critical thinking. I think critically that this means AI matured. It's good. If people complain, if people realize that AI is not good for everything, actually I think that is a growth path for AI. Otherwise it's becoming dumb. And so I look forward. It's in German, again, we have this phrase that you want to be the little sand corn in a mussel that turns into the pearl, right? So you want Reibung and you want some dirtiness in there and not everything just beautiful from the beginning. So I criticize AI, but I hope only to make it better. Even better, sorry.
Yeah, thank you very much for your talks. I have a question about the combination of sub-symbolic and symbolic methods, because there are different ways, of course. One of the ways is we know that some tasks are much easier solvable with symbolic methods like constraint solving and so on.
Yeah.
So there can be just a basically combination where you have subtasks and you use another way, like you showed, to include directly into the methods and integrate inside of neural networks or vice versa. So where do you see more potential in this direction?
Okay, I see two avenues with high potential. So one is, well, how much can we really make everything continuous? And why I think that is interesting, it's maybe it really helps, you know, the engineer department was crying and saying, but we discretize everything. So now making everything continuous is fun to see. Do we really have to make everything finite? But to be honest, I think what is from a computer science perspective maybe much more interesting is to have a system that decides on the fly whether this should be discrete and calling that, or continuous and that. And I would rather like to have something like that. It feels to me. But yeah, so I think the combination is the more interesting in deciding when doing what. That sounds more interesting to me.
Thanks.
Thanks. Coming from this discussion, I have a question. When I was in school, the calculator came. So the teachers told us that's the end of mathematics. And I went to university, the computer came up. Again, people told that's the end of a lot of engineering tasks. Now with the AI, it's again, yeah. So is this similar, or is it much more powerful? That's the first question. So is it again threatening the fundamentals of research in the end? Because some of the people, they say maybe in 10 years time we do research as a hobby, like playing golf or going cycling, because the AI will do the rest. So this is an extreme position. Second question relates to the idea of the education. We are absolutely sure at TU Wien, and I'm happy that Gerti put this up, we have the AI for all in at least since in a half year. It's for all faculties, yeah. But what strikes me from a management level is what infrastructure and which licenses do we need?
Yeah.
Because at the moment, the question for me is, will the tech giant development be so fast compared to what we do here that in the end we still need to, because you said the people need to use it, yeah? And how much do we get in this trap of we already are in, for example, for SIP and all the systems where we cannot step out anymore because of that? So this is the two questions. Is AI a fundamental difference between this calculator computer stuff thing, and will it change research from your perspective extremely? And the other one is, what do we need as infrastructure, and how much will that cost in the end for us?
Yeah, so I see large differences to just a smart calculator, because the calculator was giving you answers to standard computations. What the dream here is going back to Neural and Simon, the very grandfathers of AI. So what they want to have is a general problem solver. So a bit like all of us. So you're not growing up knowing that you will become president of TU Vienna, right? So you grow up, and then at some point you learn how to be maybe the president of TU Vienna. You get a bit instructed. So I think this is what the dream is and what we can see here. So you get general problem solvers. So it's different, but it doesn't mean that there's no space for humans or that they take over humanity. And there's also, in my opinion, no belief. You should not believe that there's no research anymore in the future. There will be plenty of researchers, but the way of doing research is changing. And so all I'm saying here is conditioned on, let's accept that AI is there. If we still debate, is there AI, is there maybe an impact, then it will be too late, and then it will have heavy impact on our economy. So I'm not saying like AI is solving everything, but a human with AI together can be more powerful. And that's our chance here, because we don't have a young society, we don't have many resources, but we have our brains. Now, how to do that? So you know that we tried to invest earlier at TU Darmstadt into the compute infrastructure. We still are not allowed to use it for inference, but that would be one option. So you buy or you use open source models and you can run them locally. If maybe meantime, what I would love if governments could give us the money for GDPR compliant licenses. So at least OpenAI is giving you a quite expensive, how's it called, enterprise. I think it's the enterprise license. There are places in the world that do that. So the Emirates, everyone has access to ChatGPT. Whether we want to fund this particular person, I don't know. There may be maybe Mistral. What about Mistral models at least? Now, the third answer, or an answer to the third question you haven't really asked, but I think it's there, is I hear always it's over and we can only buy. But China was just putting a lot of money, and within 10, 15 years, they are now on par or better than the US. So why don't we put money in there? And I strongly believe that computations don't have to be done with nuclear power plants only, but maybe also with nuclear power plants. But I strongly believe we are all smart enough. There's no magic. I mean, it's scaling what they do. It's boring scaling. So if politics wants, we can do that in Europe. Now, it's money. That's the issue, right? So maybe with open source models and a local compute infrastructure, that's already something we can do. Otherwise, maybe we have to talk to the companies, and there's not only OpenAI. But it's a political decision, and if I don't understand. I mean, they put now how much money into the oil again, just because there's the oil crisis, so there is money. Why can't we put it into research? And AI is part of it, but it's one tiny part of it, right? I mean, AI will not solve the engineering problems. So yesterday I was talking to one of my colleagues, shouldn't we get the new production line? Where can AI help? Try to understand, where do we need humans in the new production line? So that's not AI, that's production. That's what we have to do. Medicine is still medicine, and it's not just AI. It's like saying what Texas Instrument would be engineering. I don't think so.
Are there any further questions? Although this was already a very good answer. Okay.
Hello. Thank you for the presentation. I just had two questions. The first one is that you mentioned about the breakthroughs, that sometimes people overemphasize those kind of breakthroughs. And if you have a list, like of the most important breakthroughs of the last years, I don't know, 10 years or so.
Yeah. Okay.
And the second question is about, it's like related to a follow-up question from the previous ones. Do you think that in the future, like knowing notions will not be considered an advantage anymore? Like if you think about it, like today learning, like knowing logarithms, how to calculate logarithms quickly, it's not very useful because calculator, right, substituted it. And do you think that at some point knowing notions will be not useful anymore?
Okay. The list of breakthroughs, it's a very political one, and I don't know. I mean, yeah, we can list things like that's why this is there. Maybe that was a breakthrough, maybe. But then I know there's other work 5 years earlier doing very similar stuff, and no one talks about. So if you ask for a list of papers that are breakthroughs in AI, hard for me. For backpropagation, by Jeff Hinton, definitely not a breakthrough. That has been done before, and in mathematics you would call it the rule of differentiation. I mean, I'm sorry, and now he gets a Nobel Prize for that. So I would love to abstain, because this is like history of science will tell us what was a breakthrough, because it's good to write a book or whatever. For the second part, I would like to first argue that knowing logarithms is maybe still useful for some. So if you have to be very fast, there is no way in computing the logarithm on the fly because it's too slow, and then you will need to have a lookup table. But many students, they don't know that anymore, and they go for calling the logarithm again and again. Then they say, oh, I use a dictionary, but dictionary means I'm calling a Python standard dictionary, which is not the standard lookup table. And so they say, Kristian, it's not fast enough. What you're telling us is wrong. So I think knowing is still good. But I also know when I did my military service, people were also saying you have to know how a tank works. I'm still happy that I don't know how a tank works. So isn't that innovation? You improve, and because you improve, you don't have to keep everything in your mind. So yeah, I mean, some notions we will not know anymore, but then maybe there's the one moment where knowing it is important again. It's a very, I think that's why it's good that we have many human beings, and you care about something different than me, and so hopefully as a society we preserve the knowledge. But preserving knowledge is important. So I feel like in the European society we have, or political system, we currently have many people that want us to forget, and I don't want to forget.
I think this was really a very good final word.
Good.
Thank you again for your presentation.
Thank you.
And thank you for being here.
Thank you for the invitation.